Okay, today, in most cases, I'm wearing a Bluetooth so that when I walk away from the microphone, which is recording this, that it hears me. Unless you've been in this class before, today is probably the most different kind of thing that you can remember learning in a math class. Okay, it's very different. The title of the lesson is complex numbers, but in truth, you get to complex numbers by introducing what's called imaginary numbers, and imaginary numbers, again, can be kind of mind-blowing. So let's take this example, which is something we could solve this quadratic equation because there's no x to the first term, no linear term, by isolating the squared term and then taking the square root of both sides. But then we have to take the square root of a negative number. How do you take the square root of a negative number? I mean, if you think about it, a positive times a positive is a positive, and a negative times a negative is a positive. So how could you find a number that multiplied times itself would equal a negative? So, if we were using calculators, sorry, we're not using them yet, but if you put that in, you're just going to get an error. It's going to say, actually what it's going to say is non-real answer. It's not that there's not an answer, but there's not an answer that is a real number. Okay, so the way we deal with the square root of a negative is we introduce I squared equals -1, which means I, that's the lowercase letter I, equals the square root of -1. I is imaginary. Now, before we dig deeper into what is I, as long as we've defined I as the square root of -1, then when we get to this step in the problem that we're looking at, if you get to the square root of -24, you get around that by taking the minus outside, and outside the radical, it's I. So the square root of -1 is I. And then you have to simplify the square root of 24, 2 root 6. Now, in a way, it's unfortunate that we use a word like imaginary because it makes students think that it's like we're just making this stuff up and it isn't practical, but it is practical. There's a couple different examples I can give you. First, I remember when I was going to Penn State to get a bachelor's in meteorology, and I was in a class called micrometeorology, and we were studying radiative transfer. Essentially, what we were trying to figure out is, we know that the atmosphere, what we feel here, is not heated directly by the sun, right? Actually, the atmosphere is pretty much transparent to sunlight, shines through. The heat is absorbed by the Earth, and the Earth re-radiates in different wavelengths that the atmosphere can absorb. And that takes some time. It's not an instantaneous process. So we're trying to figure out how much of a delay should we expect between maximum sunshine and maximum temperature. So we modeled it. We modeled it with partial differential equations, something you'll get to about 4 or 5 classes down the road. And those partial differential equations had solutions that involved I. Okay? And the end result of all of this was it predicted that we should expect the maximum temperature 1/8 of a cycle after the maximum sunshine. So think about on a daily basis, what's 1/8 of a cycle? 1/8 of a day. 3 hours. So let's see, if the sun is overhead at noon, that would tell us that we should expect the maximum temperature at 3. And in the summer, because the daylight savings time is the sun is overhead at 1 and maximum temperature is at 4. Does that seem about right? It does, right? Okay, think of it on an annual basis, right? What day of the year do we get the most sunshine? June 21st, the summer solstice, okay? Do we get the warmest temperatures of the year in June? No. But what's 1/8 of a year? 1/8 of 12 months. It's a month and a half, about 6 weeks. So go about 6 weeks after June 21st. Now you're at the end of July, beginning of August. Is that about when we get the maximum temperatures of the year? Sure is, right? So we modeled this process with partial differential equations that had solutions that included imaginary numbers, and we got a very intuitively good feeling solution, which doesn't always happen when you model things with math. Sometimes you get a stupid answer, and you say, well, we better go back to the drawing board. But this time we didn't get that kind of answer. We got a good answer. And the other example that I've got, which I just read this in a book recently. I might have told you about the book. It was called The Grapes of Math, kind of like the grapes of wrath, right? And in that book, he gave a lot of good explanations for things that we learn in a course like this that I personally didn't know and found pretty enlightening. It's like, man, I really need to share these things. But I gave that book to a kid. He's not around here. And I don't have it to like look it up. And in fact, I Googled it to see whether I could find that particular explanation, and I couldn't, and which I find kind of odd. But in fact, what it said is that people use imaginary numbers in what's called the complex plane, which we may see a little bit at the end of this class today, to model rotational processes. Physicists use it to model rotation. And it's something you need to look at the complex plane before you understand that. But there are practical uses for these imaginary numbers, even if we call them imaginary. You know, maybe we should come up with a better word than imaginary, because it makes students think that we're just wasting time. They're making up stuff here that's not real, but it's real. So imaginary numbers. All right, now that we have imaginary numbers, we can solve problems like this, right? We can take the square root of both sides and we get to that point of having the square root of a negative. We get around that by taking out an I. And now there's no more negative inside. So you should try to do the number 2. Solve, just like I did on the one on the left. So pretty straightforward, not much to do, right? X equals plus or minus I times the square root of 38. Could you simplify the square root of 38? I mean, 2 times 19. That's it. Now there may be a little something more to do, like you've got to isolate the squared term first. So I'll do the one on the left. If I add 8 to both sides, I get x squared equals negative 28. And then I take the square root. X equals plus or minus the square root of negative 28. So x equals plus or minus I times the square root of 28. And then 28 is 4 times 7. It has a perfect square factor. So this is and usually if you're simplifying a square root of a negative, and like we had a number that could be pulled out in front, you usually write it the number, then I, then the radical. 2I times the square root of 7. So try to do the one on the right, doing the same thing. Isolate the squared term, take the square root of both sides, simplify using I. So add 7, 3x squared equals negative 24. Divide 3, x squared equals negative 8. X equals plus or minus the square root of negative 8. X equals plus or minus 2I root 2. Right? The negative comes out as an I, and then 8 is 4 times 2. So square root of 4 is 2. Now, in both of those cases, the last slide and this slide, we got an answer, and it was one term, and the term had an I in it, right? The bigger set of numbers, the thing that is the title of this lesson is called complex numbers. And complex numbers don't just have an imaginary term. They could also have a real term, right? Now this is a standard form of a complex number. It's not something that's tossed around, like I'm making it up and somebody else uses something different. It's part of the SOL that we're supposed to know that you write complex numbers as A plus BI, where A and B are real numbers. That means that the A, the first term, is a real part, and the BI is the imaginary part. You always write the real part plus the imaginary part. That's what we mean by standard form. And every one of the homework problems, I think it says, do this and put it in standard form. Leave it in standard form. Everything is about standard form. A plus BI. Uh-huh. What's that? What's that? B is real. But a real number times imaginary makes the whole thing imaginary. That makes this term imaginary. Now, there's a few cases here, right? If B equals 0, and this A plus BI, if B equals 0, then it's all A, and it's all real. So real numbers are complex numbers with B equals 0. If B does not equal 0, then you've got an imaginary number. Now, if the A equals 0, right, then it's all BI. There is no real term. It's only an imaginary term, and that's called pure imaginary. It's not a real part. It's only an imaginary part. So you could say the ones that we did on the last two slides, they were pure imaginary. There was only one term, and it had an I in it. Up till now, if you had any concept of numbers, you probably thought real numbers was the big set of numbers. That's everything. Rational, irrational, integers, all that. But it's not. Complex numbers, the big set of numbers. Real numbers are just a subset of the complex numbers when B equals 0. Are we okay? Okay, Emily? That other Emily too. Good. Now, remember when we were solving, first we learned to solve quadratic equations by factoring. Then we learned to find the zeros of quadratic functions. And we learned that if you graph a quadratic function, then the x-intercepts are called the zeros, right? And it's kind of like the same thing as the roots of the quadratic equation. And we saw two different solutions. One was we got two answers, and the other one we had a perfect square trinomial, so when we factored it, we really only got one real number solution, right? But actually, this is the one that you get with imaginary numbers. That's what it looks like. If you have a quadratic function and the zeros are imaginary, it means that it doesn't actually cross the x-axis. It doesn't mean that it doesn't have any zeros. It means they're not real numbers, because zeros that are real numbers show up as x-intercepts, right? The x-axis is an axis of real numbers. So either a parabola that opens up, which is already above the x-axis, or a parabola that opens down, which is already below the x-axis, both of those would have imaginary solutions. And the other thing that we emphasize more in the next chapter when it comes to polynomials, but you always expect in any polynomial the same number of complex solutions as the highest power of the variable. So in a quadratic, we expect two answers. There will be two complex answers. In this case, they're both real. In this case, it's only one distinct number, but because it comes from a perfect square trinomial, it actually occurs twice. And in this case, two imaginary. But in any one, they always have two. And when we get to cubic functions, it'll be three. Right? Some may be real, some will be imaginary. I don't know if So most of what we're supposed to get out of this is we need to know how to do operations with complex numbers. Add, subtract, multiply, divide. And then we need to know how to raise I to a power. That's its own SOL. So that's what we'll be doing here. And I'm going to do a couple on each, I'll do something and then I'll have you do something else on the same slide so you'll have it right in front of you. The top is kind of just telling you what to do, right? How do we add and subtract complex numbers? You add and subtract the real parts, you keep them separate, and then you add and subtract the imaginary parts. You treat them like terms, right? If I'm adding i's, you could just think of it like, negative I plus 4i, we'll treat like it's negative x plus 4x. I mean, you just add the coefficients. So to add and subtract complex numbers, add the real parts, add the imaginary parts. So it looks like this. Right, these parentheses on letter A don't do anything for us. So 8 minus I plus 5 plus 4i. Okay, I need to add the real parts. What are the real parts? 8 plus 5. And then I need to add the imaginary parts, negative I plus 4i. So that is 13 plus 3i. Okay, when you subtract complex numbers, understand that complex numbers could have two terms, right? A real term and an imaginary term. And when you're subtracting in front of parentheses, you've got to be careful to distribute the minus. That's going to make that a plus 6i. I mean, that's most likely where you'll make the mistake here. Right? Make sure you distribute this. So I'm going to take a step and distribute that and lose the parentheses. So this is going to be 7 minus 6i minus 3 plus 6i. So the real parts are 7 minus 3. The imaginary parts are negative 6i plus 6i. So 7 minus 3 is 4. Negative 6i plus 6i cancel. So the answer is 4. You don't need to write 4 plus 0i, you just say 4. That's it. So why don't you try the last one, if you didn't already do it. Okay, so distribute the minus. If there was a mistake, a fair number of people did that. 10 minus 6 minus 7i plus 4i. So the real parts are 10 minus 6. The imaginary parts are negative 7i plus 4i, which is minus 3i. Okay. Multiply. So when you multiply imaginary numbers, you could either have, well, actually, it could be even simpler than this, but this is an example of one term, monomial times binomial, which means you're going to use distributive property, right? This is an example of a binomial times a binomial, which means you're going to FOIL, okay? Now, I'm going to do this one, and then you'll do that one, and then I'll do this one, and you'll do that one. So let me do the letter A first. Okay, it's distributive property, so I'm going to go 4i times negative 6 and 4i times I. Okay, so watch this. That'll be negative 24i. And what do you get when you multiply 4i times I? 4i squared, right? But what does I squared equal? Negative 1. Remember, I is the square root of negative 1. I squared equals negative 1. So replace the I squared with a negative 1. So now we have negative 24i minus 4. But that's not standard form. We need to put it in standard form. How do we put it in standard form? Switch the order. It needs to be the real part, then the imaginary part. Negative 4 minus 24i. A plus bi. Go ahead, try the 11. Let's distribute again. I times 9 is 9i. I times negative I is minus I squared. So replace the I squared with a negative 1. We'll get 9i minus negative 1, which is 9i plus 1. And then we will switch the order so that it's in standard form. 1 plus 9i. Okay, now that on the top, because it's a binomial times a binomial, you're going to FOIL, right? In one way or the other, whether you use FOIL exactly, just make sure everything in the first set of parentheses multiplies everything in the second. So it'll be negative 36 plus 63i plus 8i minus 28. Oh, sorry, I'm thinking of something different. Getting ahead of myself. Minus 14 I squared. I mean, you can see that the imaginary parts are going to be these two. And then that you have to turn into a negative 1 so that you can combine that with that. So this is negative 36 plus 71i minus 14 times negative 1, which is negative 36 plus 71i plus 14, which is negative 22 plus 71i. Does it look right? So do the 12. So it should have been 16 plus 2i. So let's see, we did add, subtract, and multiply. What do you think is next? Oh my gosh, how do you know? It's a miracle. So now we divide. And when you divide, we talked last time about rationalizing a denominator by multiplying by, dependent on the situation, the square root of the, that was in the denominator over itself, or if there was more than one term, by the conjugate. Well, when you have complex numbers, the conjugate is called a complex conjugate, but it's basically the same thing, right? The complex conjugate of 1 plus I is 1 minus I, right? The complex conjugate of 3 minus 2i is 3 plus 2i. You just switch the sign in the middle. The complex conjugate of 1 minus 4i is 1 plus 4i. So in order to get rid of the imaginary, which is making the denominator not just irrational, but imaginary, we're going to multiply by the complex conjugate divided by itself, right? So in the first one, it'll look like this. 1 minus I, 1 minus I. And in the numerator, that's a distributive, right? 5 minus 5i. Pretty straightforward. In the denominator, I'm going to FOIL this out, at least this time, just to show you. But then in the end, we don't need to FOIL this every time. Okay, if I'm FOILing, 1 times 1 is 1. 1 times negative I is minus I. 1 times positive I is plus I. And I times negative I is minus I squared. Whenever you multiply by conjugates, the reason you do that is because it cancels the middle two terms. They will always be opposite of each other. So in terms of FOIL, the O and the I cancel each other. So you don't need to do FOIL. You could do F and L. Do the first terms and do the last terms, right? Because these two will always cancel. So this is 5 minus 5i divided by 2. You could split that into two terms, 5 halves minus 5 halves I. That's okay. Now, what would I multiply the number 14 by to make the denominator not imaginary? What should I multiply by? 3 plus 2i. Again, the numerator, you're still going to have to FOIL. Right? That'll be 15 plus 10i plus 6i minus plus 4i squared. In the denominator, I'm not going to FOIL. I'm just going to do first terms minus last terms. So that'll be 9 minus 4i squared. Nothing wrong if you want to FOIL. Okay, and I'm just going to take a little bit of a shortcut here. 4i squared equals what? Negative 4. Negative 4, right? The I squared will be negative 1. So this is going to be 15 minus 4 is 11 plus 16i. And 4i squared will be 4. 13. So try this one here, which doesn't have a number. Okay, so this looks like 1 plus 4i. 1 plus 4i. And the numerator is a FOIL. That'll be 7 plus 28i plus 5i plus 20i squared. And the denominator, again, I'm just going to do first terms minus last terms. The product of the first terms minus or plus the products of the second term, last term. So this will be 1 minus 16i squared. So this is 7 plus 33i minus 20 divided by 1 plus 16. So the final answer is negative 13 plus 33i divided by 17. Okay. Okay, Nick? Okay. So the last thing, we're almost done, I think, is we're supposed to know the power, how the powers of I work. And the thing is that it's actually just a repeating pattern. Notice I to the first is I. I squared is negative 1. We've already dealt with those two. I to the third would be I squared times I. Well, that would be negative 1 times I, which is negative I. And I to the fourth would be I squared times I squared. Thank you, Peter. I squared times I squared, which is negative 1 times negative 1, which is 1. Right? So notice the pattern. I, negative 1. Negative I, positive 1. Okay, now jump down to I to the fifth. I to the fifth will be I to the fourth, which is 1, times I. So, of course, I to the fifth has to be the same thing as I to the first. And I to the sixth has to be I squared times I to the fourth, which is 1. So, of course, I sixth is the same as I squared, negative 1, negative 1. I to the seventh will be I to the third times I to the fourth, so it'll be the same as I to the third, negative I. And I to the eighth will be I to the fourth times I to the fourth. 1 times 1 is 1. And then the pattern just starts over again when you get to I to the ninth. So really all you have to know when you're finding powers of I, which is its own SOL, students will know how to find the powers of I, is the multiples of 4. You know that every multiple of 4, I to the fourth, I to the eighth, I to the 12th, etc., is 1. Right? Every I to an even power that's not a multiple of 4 will be negative 1. Negative 1. If I go to I 10th, negative 1. Right? If I raise I to 1 more than a multiple of 4, like 1 or 5 or 9, I get I. That's this one. And if I raise I to 1 less than a multiple of 4, like 3 or 7, I get negative I. So you just have to keep those 4 things in mind. And most of the time, they're not going to ask you questions that are like these numbers here. They're going to ask you like big numbers that you have to work a little bit to know whether it's a multiple of 4 or is it 1 more than a multiple of 4, and then apply the pattern. So the next slide, I'll do some that are really big, and then I'll have you do some that are not quite so big, and then we're done. Okay. So, I to the 399th. It's an odd number. Is it 1 less than a multiple of 4 or 1 more than a multiple of 4? It's 1 less, right? Because 400 would clearly be a multiple of 4, right? So if I go 1 less than a multiple of 4, according to this, should be negative I. So once I've determined that, I just say negative I. And how about 4001? That looks like 1 more than a multiple of 4. Michelle, put it away. Okay. So that'll be one more. So that, what is that again? That is, one more is I. Now, the last couple, I presume one of them is a multiple of 4 and one of them is not. And these numbers aren't so hard. You could just like do the whole math. But do you know the trick for finding out whether a number is divisible by 4? If the last 2 digits are divisible by 4, then the whole number is divisible by 4. So is 88 divisible by 4? Sure. So this is divisible by 4. It's a multiple of 4 power. So what does that make I to the 588? 1. Right? And again, using the same trick, is 2 divisible by 4? No. So this is even but not a multiple of 4, which means it's -1. So why don't you try those 4? One was the multiple of 4. Say again. I to the 80th, and multiples of 4 powers are 1. So 42 is not a multiple of 4, but it's even, therefore it equals -1. Okay, which one of the last two is 1 more than a multiple of 4? Equals I. I33 is I. And let 1 less, because 120 is multiple of 4, 1 less would be 119, -I. That's it. Clear as mud? So some of this stuff, when we went over it at the beginning, it would have not made any sense at all. But after the lesson, recognize the square root of -1 is I, simplify powers of I, add, subtract, multiply, divide, complex numbers, write complex real and pure imaginary numbers in A plus BI form. And then we didn't really do that as much, but that's okay. We did talk about the fact that complex numbers is the big set, real numbers are a subset of that. So that is the end. That's the homework.